dependent variable, and that is your y variable, right? Independent variable, that is the x. Okay. So y is what you're trying to predict. So your question is on y. So you're asking a question about the value of y when you're building a regression model. So what is going to be my y value if my x value is this much? So if my x value is 20, then what would be my y value? So if I spend this much money in advertising, then what would be my sales? So this would be, so that would be like, so for example, sales level, and this might be your advertising expenditure. So if I spend this much money in advertising, that what would be my sales? So that's the kind of question we want to ask. Okay, so simple regression. Simple regression means we have only one x variable, one thing. So how do you predict the y? We're just going to look at one thing, like advertising expenditures. We're going to just use that one thing to make a prediction on the sales. Okay. Now, so we're going to take a look at the Butler trucking example that is in your book. So this is a trucking company. They have all these drivers drive around making deliveries. So you would think that the driver who has to drive a lot of miles, it's going to take him more time, to drive that route and to make those deliveries. Okay. Okay. So that is going to be, we're going to build a regression equation for that. So total daily travel time. So travel time is going to be what we're trying to predict based on the number of miles traveled. So that's what's going to be our x. So let's take a look at the data, and that the data is also on Excel file, but let's first look at the data in the PowerPoint. That is over here. And so we're going to start with a very small data set. This is only 10. So we have only 10 data points. And we have here miles traveled here, and the travel time here in hours. So we know the units of both the variables. X is in miles, y is in hours. Okay, so let's see. Let's take a look at this for a moment. So these are 10 driving assignments, and what is the shortest travel time? Do you see here? Well, what is the shortest travel time? 4.2. Oh, right. So 4.2 right here. So 4.2 hours. And how many miles did the driver have to travel? That is 50 miles. So 50 miles, it took 4.2 hours. So 50 miles is also, if you look at the miles, 50 is the shortest, right? The lowest number of miles here. So you can see there is some relationship. And what is the highest amount of the travel time? 9.3. So that is over here, 9.3 hours, and it was for traveling 100 miles. And 100 miles is the highest number of miles. And here, and there's also other 100 miles that they result in a little bit smaller travel time. So in this case, in this data set, the shortest travel time corresponded with the what's over here, 4.2. Shortest travel time corresponded with the lowest number of miles. And the longest travel time, which was 9.3, corresponded with the longest distance, 100 miles. And it's common sense. So if you have to travel, more distance, of course, it's going to take you more time. So you don't have to be some math genius to realize that relationship. So the thing is that now we want to actually write out the relationship explicitly in terms of x and y. Okay, so if I were to to see the relationship between the two variables, what can we do? What kind of chart would we plot to see a relationship between two variables?
Scatter.
Scatter?
Scatter plot.
Scatter plot? Okay, that's a good idea. So, okay, let's go to the Excel file over here. Okay, so here's my data, and first I want to make a scatter chart from this. And okay, let's remind ourselves which is X and which is Y. What was the miles? X or Y? X. Okay. Time was the Y. Okay. So let's make a scatter chart of this thing. So we take we take the two columns of data, right? Two columns of data, and this is in the right order as far as graphing the scatter chart, because the scatter chart in Excel assumes that the first column has your X variable. So X variable, and then followed by the Y variable. Okay. So let's go to insert, and then scatter chart over here, and let's take the first one here. So here is my scatter chart. Okay, now compare this to something like this. So what now? Some people don't really know how the scatter chart works. So when they're asked to plot a data like this, they might just use a line chart. So let's see what happens when we try to use a line chart. So I'm going to take these, and then we're going to plot a line chart. Okay. So you can see this is not quite what we want. So it just treats the two columns separately. This is not very helpful. Okay, so don't do that. So if you are analyzing relations between two variables, you want to usually you want to do a scatter chart. Okay, so we're going to take this out and work with this scatter chart. Right over here, right over here. Okay, I got it. Okay, so we should also, of course, label the axis. So we're going to do that right now. We're going to click on the, there it is, the plus sign. So we're going to say plus sign and the axis titles. And here, what's my axis title? That's the time. Okay, so let's see, time. So you go over here, say time. And actually we say hours. Always need to indicate the units. And that's the Y variable. Right, and here it's going to be the miles traveled, and that's for the X there. Okay, and here maybe you want to say something like time versus miles traveled. Okay. Now you guys, did we talk about inserting a trend line? Okay, so you guys know how to do that. So let's go ahead and do that. So we're going to right click on one of these things and go to add trend line, and then we're going to stick with a linear trend line. So that's the default, and we want to display the equation on chart. So we're going to click on this, display equation on chart, and oh, here's a free bonus, display R square. So why not? We're gonna click on that too. Okay, so it's like this. Okay, so and then we're going to exit out of this. So that's it. That's our regression equation right there. Y is equal to 0.0678 times x plus 1.2739. And R square we're going to discuss in a little bit. So basically R square tells you how good this model is, how valuable, how worthwhile this model is. So you could see here there is some relationship here. Then so when the x value is going up, that is, if I travel more miles, then the time it takes is also going to increase. So increasing the miles traveled tend to be associated with the increase in the number of hours. Now, anybody know what kind of relationship this is? Positive, negative? Right, positive. So when one goes up, the other also goes up. When one goes down, the other one also goes down. So using this, we should be able to make predictions, and also we discuss the correlation coefficient. So we talk about two variables being correlated with each other, and that means again there is a relationship. Correlation and that's R. R is like symbol for correlation, and all you have to do is type CORREL, and there it is. Then you just give it your two variables. So array just means list. Like if you have a table, that's an array. If you have a column or row, that's an array. So we're going to give it these guys and comma, and then this other column of values. Now, how do you interpret this? It's positive, so positive relationship. And so it's a positive relationship. And if the correlation was negative, then we would say it has a negative correlation. Here is a slider correlation coefficient. So is there a relationship between the time and the miles traveled? What kind of relationship? So we saw it was about 0.8 something. So that would indicate you have a positive relationship. So in general, what is the range for correlation coefficient? It's going to be a number between -1 and 1. So -1 and 1. So 1 means like the highest level of relationship. So if the correlation was equal to 1, that would mean if you know the x value, then you know exactly what the y value is. So you'll be very certain. So if you know x is 5, then you know y is 10, and then you could be very sure of that. So there's a perfect relationship between the two. Now, if it were -1, if the correlation was -1, then that would mean what? No relationship? Negative relationship. And it's a very strong negative relationship. So let's take a look at, let's see, yeah. So if it's close to -1, no, close to +1, that means you have a strong relationship. And here's some pictures. So here is a -1 relationship, correlation -1. So this would mean that as you go to the right, your points will tend to go down, right? So as the x is increased, as you go this way, your y value will tend to go down. Now compare this one to this other one. Both of these pictures have negative relationship, but when R is -1, then you're gonna see the points all lined up in a straight line. Whereas when R is -0.6, then you still have a negative slope, but the points are not all lined up in a straight line. They're kind of scattered around a straight line. So the pattern is a kind of cloud around some line, around some straight line. And now, if R is equal to 0, 0 would mean zero relationship, no relationship between the two variables. Then you will see a picture like this. When x is changed, y values are just kind of dancing around. Sometimes it goes up, sometimes it goes down, but it's just it kind of evens out. So here, as x is as you go to the right, y sometimes goes up, but sometimes goes down. And so you don't really see a pattern here going on. Then you say there's a relationship. So this means if there's no relationship, then it's useless. Okay. Then there is no point in trying to build a relationship when it doesn't exist. Okay. And these other two pictures are for positive relationships. So you could see here when R is equal to 1, all these points are lined up perfectly in a straight line. So if you know the x value, then you know exactly what the y value would be. Whereas here, R is equal to 0.6. It's a positive relationship, and it's not as strong. It's not as strong. It's kind of scattered points around a straight line. Okay. Okay. So going back to the previous slide. To review. Okay, -1 or 1, close to -1, so then you have strong relationship between the x and y variables. Close to 0, then no relationship. And so positive, when one goes up, the other goes up. And negative, and then it does the opposite. So roughly, okay, the guideline. So what do you call a strong relationship as opposed to weak relationship? So here's a rule of thumb. So we might say, if the magnitude of the correlation is less than 0.3, then we say we have a weak correlation or weak relationship. So what does this mean? So it's the absolute value. So that would mean that if it's negative, it will still, so it would be like you're going, if R is, I don't know, like negative 0.3, between negative 0.3 and positive 0.3. And so that's what this is saying, the magnitude. The absolute value is less than 0.3. So then you have a weak correlation. Now if the R, the magnitude of the correlation is between 0.3 and 0.7, so it would be like if the R is between 0.3 and 0.7, or R is between what? Right, negative 0.7 to negative 0.3. Okay, so either way, you would say we have a moderate correlation. So not too close to 0 and not too close to 1 or negative 1. And the strong correlation is if its magnitude is greater than 0.7, so that would mean R is greater than 0.7 or R is less than what? Right, negative 0.7, less than negative 0.7. Then you say there is a strong correlation between the two variables. Okay, so now that we know what a correlation is, now let's discuss a linear regression model. Okay, so we saw before, okay, what was the equation? Let's take a look at it here. Here is the equation. Now, let's see. So this is what we get when we run a regression, or when you ask for an equation for the trend. This is what we get. So in this case, okay, it was 0.0678x plus, and what was it?
1.2739.
1.2739. Aha. Okay. Thank you. So that's our estimated regression. Estimated regression. Okay. Now the order is a little bit different here. So the Excel gives you this term first. This term is this part, and then this term is this other part. Now I mean both are equivalent. So what does this do? This gives us an estimate of the relationship between the x and y variables. And what is now? Is this definitely the correct relationship? No. It's just based on 10 points. It's just 10 rows of data. So this is just an estimate from a sample of data. Now, in general, this trucking company has a lot of driving assignments, not just 10. So 10 is just 10. We just have a sample of 10. So based on a sample of 10, we came up with this regression equation. But in general, there's going to be a lot more driving assignments at this trucking company. So if we were able to have all of the data, not just 10, but like all the driving assignments ever, then we might have a different regression equation. So the regression equation that's based on all the possible data would be written as something like this. And so what's the difference between that one and that one? The notation is that, well, this one from the sample has Roman letters, and the other one has the Greek letters. And what is this little error term here? The error term accounts for the variability. For the variability in y that cannot be explained by x. So by that, what we mean is when we look at our data. Okay, so miles driven. Let's say this assignment drove for 100 miles. It took 9.3 hours. Here's another assignment that has the same number of miles. Drove for 100 miles. It took 8.9 miles. Drove for 100 miles and took 6.5 hours. So just because 3 assignments involve same number of miles, it doesn't mean that you get the same amount of time for each assignment. Why is that? Why shouldn't you get the same time? Why shouldn't you take the same time if it's the same distance? Right, various factors. So there's other factors. Right. So not just the number of miles, but maybe traffic. Oh yeah, that's traffic. That's a very important factor. So there's traffic, and maybe like as you drive, like sometimes you have to make only one delivery. Sometimes you may have to make several deliveries. So there's also number of deliveries that the driver has to make on the truck. And the weather. So there's a lot of other factors, right, that we're not accounting for here. And so there will be a variability in the time it took. So even for the same number of miles, the time it takes is going to vary based on some other factors that we didn't take into account in our model. So this part is for all the other stuff. All the other stuff we didn't account for. Okay, so this will be the part based only on the x. And then this part from something else, from other factors that are not accounted for. This is kind of probability notation. So what this is saying is expected value of y given some x value. So it's basically the average y value given some x value. So for instance, if you were to ask, what is the mean or the average driving time for, let's say, for 60 miles for a trip that is 60 miles long, then you would write it like this: E of y given 60. So it's the average of the y value given you are driving for 60 miles. Okay, so that's basically your average. So yeah, that's be your average. So when you drive for 60 miles, sometimes it might take 5 hours, sometimes it might take 6 hours, but if you were to average all those values, and that's kind of the theoretical idea, this would be the average of all the trips that require whatever, like 60 miles or whatever given value is. This is like the best we could do. This is the best we could do, okay, trying to estimate this part, the average, the driving time for some given x value. So how do we use this? Okay, what if x is 60 miles? Then what is the y? We will just plug it in: 0.0678 times 60 plus 1.2739, 5.3419 hours. So this will be like the average we would expect. So if you were to look at the driving assignments that was 50 miles, on the average you would expect it to take about 5.34 hours. So this gives you the prediction of the mean, prediction of the average. So that's how we would use the regression equation. So again, this part here is kind of the ideal concept that since we don't have the population, we'll never be able to get the regression for the population, but we're going to just estimate it by using our sample data, which is kind of small sample data that's drawn from a population. Okay, and what do you call this? This is called the y-intercept. Y-intercept, b sub 0, and b sub 1 will be called the estimated slope because it's multiplied by the x variable. So if I were to maybe extend this line, so that should be about 1.27 over there. Here, 1.27. So that should be the intercept, right? So that's your b sub 0, and then so that's this part, right? So that's your b sub 0, and b sub 1 is the slope here, 0.0678. 0.0678. Remember this, what the slope was. So slope is what over what? Rise over run. Oh, thank you. Okay. So that tells us that we have a slope is 0.0678. So that would mean, let's see, So if the mile, so this would be like a for each mile. So for each additional mile, so that is x is increased by 1, then how much will y increase? We would just look at the slope, right? 0.0678. So we would say the time, or the hours will increase by 0.0678. Hour, it's kind of hard to make sense of it. So maybe change it to minutes. Multiply 60, right, to get the minutes. So 4.06, about 4.068 minutes. So about 4 minutes. So this would mean, like each additional mile that you have to travel, it will take you about 4 minutes. It will take you about 4 minutes more. So we just discussed it. The slope is the estimated change in the mean of the dependent variable. All right, so this was 0.0678. So it would be like the estimated change in the mean of the dependent variable. So dependent variable was the time, and so this is like 1 mile more. 1 mile more. So 1 mile more led to 0.0678 hours, and that gave us about 4 minutes. So it tells us like 1 more mile, it'll take you 4 more minutes. And what about the y-intercept? And this was about 1.27, right? About 1.27. And by the way, what is the unit here? 1.27 what? So what was the unit for y? Time, right. So it was in hours. So this part must also be in hours. So intercept, will be the same unit as the y. So this is also hours. So this would mean 1.27 hours. Okay, so this is saying if x is equal to 0, then the y value will be about 1.27. So when x is equal to 0, then y value will be about 1.27 hours. Now, this would be like how many miles you travel. So now, does that make sense? If you don't have to travel at all, okay, if there's no miles, 0 miles, then the driving time will be 1.27 hours. But you could perhaps interpret this as a sort of a time that is not related to driving, related to the number of miles. So there is the number of, so there is a component, 0.0678 times x. This part is multiplied by the number of miles. So you could think of this part as a driving time on the road, because this part is proportional to the number of miles. But then sometimes you have to stop and make a delivery, and sometimes you have to go to use the restroom or whatever. So there's these other times that are not related to the number of miles. So maybe that part it belongs to the intercept. So we could think of 1.27 hours as the so that's the time that is not related to the distance. Like when the driver is stopped and making deliveries and things like that. Okay. So one kind of caveat here is when you have the regression equation, you don't want to extrapolate too much outside the experimental region. What does that mean? The interval. Interval where your data came from. If I look at my data, what is the smallest number here? 50, right? So here the experimental region is x value of 50 through what? through 100. Okay, so within this range, feel free to make predictions. Plug in any number between 50 and 100, stick it in here, and make the prediction, and that's fine. But if I plug in, let's say, 150, then it's a little bit risky. So because we know, like between 50 and 100, we know it follows a certain pattern. It follows kind of straight line pattern. But beyond that, we can't really be sure. Beyond that, we can't be sure that the same pattern continues. So what I mean by that is, if I go to the picture, now here we could kind of assume that the in this region it looks kind of like a straight line is reasonable, but maybe if I go very far, maybe this will kind of change. Maybe this will change to something like this. Maybe it'll flatten out, or maybe it'll go even higher. So we don't really know how the data will act beyond this part. So you want to try. So you want to kind of try to avoid making predictions when you are too far from your data, too far from the interval of your data. I mean, a little bit beyond is okay, but don't go too far.